Hello everyone, I'm Xie from the University of Houston. Together with my postdoc advisor Roland and collaborator Eric, we would like to talk about landslide characterization using hybrid Spaceborne and Airborne InSAR and pixel tracking. Our study site is the Slumgullion landslide in Colorado. It's credited as an ideal natural laboratory to study the mass wasting process. It moves at a couple of centimeters per day, and that is 7 meters per year since its reactivation 300 years ago. It travels about 4 kilometers downhill like a snake. And here we have 4 independent Airborne and UAV flight lines collected by NASA JPL between 2011 and 2018. We also have C-band Sentinel-1 satellite data. The red and blue boxes show the footprints of the ascending and descending tracks, and we applied hybrid InSAR and pixel tracking method and generated more than 1,000 pairs, 2 orders of magnitude larger than previous studies. We also have in situ geodetic and hydroclimate data, and they constitute an unprecedented collection to study the slow-moving landslide. There are 2 essential advantages of Airborne system, which are the submit-level resolution and the flexible flight lines. There were 1 to 3 UAV campaigns every year between April and November during times of no or less snow cover. For Sentinel-1, it was not until the mid-2017 that the satellites began to collect the data over this area more regularly with a 12-day interval. The data metrics in terms of the pixel spacing, wavelengths, and the temporal resolution are especially important for our study, and they directly determine the feasibility of InSAR and pixel tracking methods. Say the limits of InSAR is 1 fringe per pixel, and therefore we set the upper bounds for the temporal baseline. As for POT, the displacement needs to be larger than the accuracy, which is about 1/20th to 1/10th of the pixel size. But it also needs to be smaller than about half of the matching window size. Otherwise, there will be too small overlapping area for a robust cross correlation. We constrain the temporal baseline and apply the specific matching window size for the flight lines along and across the slip direction of the landslide body. The hybrid InSAR and pixel tracking methods help reduce horizontal rotation over the head and the advanced movement of the emergent toe. The time series results agree well with 3 extensometers installed at the lateral shear surface. Then we pick up a total of 77 transverse profiles and extract their longitudinal velocity as shown in the y-axis. We found the middle and narrow neck of the landslide has the largest rate of 14 millimeters per day. We then constrained the slope channel geometry, surface and subsurface velocity for each profile by integrating the non-Newtonian model. As for the temporal response to the climate variables, Sentinel-1 results show that the landslide head in circle slowed down abruptly due to the low water year of 2018, while the changes at the toe are not that evident. For the long-term UV results, we apply an exponential equation to quantify and differentiate the slowdown and speed-up process for each of the 12 kinematic elements. Since 2013 and 2018 are low water years, we separate out 3 time spans and use their respective time series to constrain the coefficients of this exponential model. The exponent k is negative during the first and third time frames, suggesting slowdown, and which is in contrast to the middle time frame. It's also interesting that the head is always the most sensitive, no matter acceleration or deceleration. We believe this is because the head is very shallow, and thus the changes in pressures come sooner and in greater magnitude. So I have to leave out our summary here. Please refer to our recent papers for more information about our observations, methods, and models. Also, please email me with any questions. Thank you.